Hi, we will talk about the pressure derivative trends for other common flow regimes. The group members are Amanur Abu and me, Kanju A. Makapagal, and lastly, Kaiser Ulama. So now, pressure derivative method. The type curve technique to while testing data analysis was created to help identify flow regimes during the well-bore storage dominated phase and infinite acting radial flow. Below is the example of data analysis. And type curves for a well with well-bore storage and skin in a reservoir with homogeneous behavior. So now, let's talk about the benefits of using a pressure derivative type curve. The first one, on derivative plot, heterogeneities that are hardly visible on the conventional plot of well-testing data are amplified. Second, on the derivative plot, flow regimes have distinct characteristics forms. Third, the derivative plot can illustrate many distinct properties in a single graph that would normally need many charts. And lastly, the derivative method increases the definition of analysis plots and as a result, the interpretation quality.
The pressure derivative as the derivative of dimensionless pressure PD with respect to dimensionless time TD over dimensionless storage factor CD. By simplifying it, we can get dimensionless pressure multiplied to the quantity of TD over CD, so we can get 1/2. Derivative plot of dimensionless pressure times the quantity of TD over CD versus TD over CD for the entire well test data will produce two straight lines that are characterized by: first, a unit slope straight line during the wellbore storage dominated flow. Second, a horizontal line at dimensionless pressure multiplied to the quantity of TD over CD is equals to 0.5 or 1/2 during the transient flow period. So, according to Chaudhry 2003, this shows the pressure derivative trends for other common flow regimes. So, figure 10.6 shows pressure derivative trends for common flow regimes. So, first, wellbore storage dual porosity matrix to fissure flow. So, semi-log straight lines with slope equal to 1.151. So parallel straight line responses are characteristics of naturally fractured reservoirs. So next, dual porosity with pseudo-steady state interporosity flow. So pressure change slope, increasing leveling off, increasing pressure, derivative slope equals to 0, valley is equals to 0. Additional distinguishing characteristic is middle time valley trend. Duration is more than one lag cycle. So dual porosity with transient interporosity flow. So pressure change slope. So steepening. So pressure derivative slope. Upward trend is equals to 0. Additional distinguishing characteristic, middle time slope doubles. So for steady state, pressure change slope. So for drawdown and 0 for build up. Pressure derivative slope for drawdown and steeply descending for build up. Additional distinguishing characteristic, late time drawdown. Pressure change and derivative are overlain. Slope of one occurs much earlier in the derivative. Constant pressure boundary, steady state. Pressure change slope going to 0. Pressure derivative slope going to steeply descending. Additional distinguishing characteristic cannot be distinguished from pseudo-steady state in pressure buildup test. So, single ceiling fault, pseudo-radial flow. So, pressure change slope, steepening, pressure derivative slope going to 0, and upward trend is 0. Additional distinguishing characteristic is late time slope doubles. So lastly, elongated Buffet reservoir linear flow. So pressure change slope 0.5, pressure derivative slope 0.5. So additional distinguishing characteristic late time pressure change and derivative are offset by factor of 2. Slope of 0.5 occurs much earlier in the derivative. So figure 10.6 illustration of pressure derivative trends for other common flow regimes.
According also to Chaudhry 2003 for the pressure of derivative trends for other common flow regimes, in this figure, the well storage dual porosity matrix to Fisher flow says the semi-log straight lines with slope is equal to 1.151. Parallel straight line responses are characteristics of naturally fractured reservoirs. And next is the dual porosity with pseudo-steady state interporosity flow. In this, the pressure change slope is increasing, leveling off increasing. Pressure derivative slope is equal to 0, the valley is equal to 0. Additional distinguishing characteristic is middle time valley trend. Duration is more than 1 log cycle. For the third is the dual porosity with transient interporosity flow. In this, the pressure change slope and the pressure derivative slope is upward trend is equal to 0. Additional distinguishing characteristic is middle time slope doubles. For the last figure is the pseudo-steady state. Pressure change slope 1 for drawdown and 0 for buildup. Pressure derivative slope 1 for drawdown and steeply descending for buildup. Additional distinguishing characteristic is late time drawdown, pressure change, and the derivative are overlain. Slope of 1 occurs much earlier in the derivative. And according to others, the Weber storage infinite acting radial flow is where the pressure change slope is equal to 1, the pressure derivative slope is equal to 1. Additional distinguishing characteristics are early time pressure change and derivative are overlain. In the Weber storage, partial penetration, infinite acting radial flow, the pressure change increases and the pressure derivative slope is 0. Additional distinguishing characteristic is middle time flat derivative. In linear flow in an infinite conductivity vertical fracture, where K times X sub F squared, calculate from specialized plot, the pressure slope is equal to 0.5 and pressure derivative slope is equal to 0.5. Additional distinguishing characteristics are early time pressure change and the derivative are offset by a factor of 2. In the bilinear flow to an infinite conductivity vertical failure, the K sub Fw is calculated from specialized plot. The pressure slope is equal to 0.25 and the pressure derivative slope is equal to 0.25. Additional distinguishing characteristics are early time pressure change and derivative are offset by the factor of 4. In the Weber storage infinite acting radial flow, there is ceiling fault rather. In the Weber storage, there is no flow boundary. And lastly, in the Weber storage linear flow, Kb squared is calculated as well from specialized plot. That's all. Thank you.